Hey, what's up, guys? Yeah, yeah, I have like some time that I haven't recorded video. Yeah, so today I want to talk about relativization of P and NP. Okay, so this is also interesting topic that I recently learned. Yeah, so the idea is that we want to show that this is like the theorem or the theory that why P versus NP is hard to prove. Okay, so the fact is that this is like in 1975, there are Baker, Hill, and Solvay prove the following theorem: prove that there exists the oracle A such that P with an oracle A is the same as NP oracle A, and but the other also oracle B such that P with an oracle B is different from oracle B. Okay, so basically this is like the Y versus P versus NP is hard to prove because if you want to use the diagonalization technique, right, the diagonalization technique can allow you to prove like P do not have the same as XP. If you learn advanced calculus, you know that Cantor developed the so-called diagonalization, which you can prove that the real number is uncountable compared to, the cardinality of real number is strictly greater than the integer rational. Okay. So these two videos, I will quickly prove about this theorem. Okay, so first one is very short video that I just proved the first one. Okay. Okay, so this one is very simple, and yeah, so the first one is very simple. So we just choose. So in order for like P, right? So P the polynomial time the with the oracle A in the same as MPA, we need to choose like we need to choose A to be super powerful, right? This is the intuition. So we just choose T to be, let's say, T to be F. Basically, this is a P-space complete language. Okay, so simple fact is that right, P is we already know that P is a subset of NP and the P space. Okay, so if you have oracle A, that you can just add it on it, right? Because however P use A and P you can use A, right? P space can also use A. Okay, so in order to show this, we need to so this is the first, and the second second fact that is very simple, that since TQBF is P space complete, so if you have P space, then I can just, if someone asks any P space language, I can just ask the oracle, right? So I can just ask A. Okay, so P space is just subsets of P of A. Then okay, then so the right, so all these are trivial, and the final is that we can show this P space A. So P space A is the same as P space. Okay, this is probably the non-trivial part, right? Because that for example, if you take NP and take NP, right, it's maybe not the same as NP, right? Because this is polynomial hierarchy. But the fact these two are the same is just very simple, because that right, because with a P-space machine with P-space oracle, this P-space don't care about time. So whenever somebody asks, whenever this P-space machine or P-space language access a P-space machine access A, then I can just use the polynomial space and solve A. And I don't care about time. This is different from like if you try to argue the NP to the NP oracle with the same as NP, you're stuck, right? Because it seems like that if you have NP oracle that you can access, there is a time constraint on it, but there's no time constraint, right? So however, if you access A in a T2BF, then you can just spend however time, right? Spend polynomial time or however, right? Using the P space, just using the polynomial space. Okay, so if you have these three, facts, then you can see this as P space, right? But as I said, that the P space is the same as P of A. Okay, so this that P of A oracle is same P as oracle, so everything in the middle should be the same. Okay, so P of oracle A and PA will the same as P space A. Okay, so this is the first part. Okay, in the next video, that's next part that we will, it's a little bit complicated, but we will find B. So we will show that there is a language B such that P to B is different from P to B. Okay, see you guys.